We're level 4. I've got 5 and then every 5-minute increments after that.
I just throw my phone across the room and have to suffer from the fact that my phone is ringing across the room.
No, I see. I put my phone right next to my head.
Yeah, so
it's
do I,
really
yeah.
loud.
That way I can't miss it.
Yeah.
Mine gets louder, I
Alright.
guess.
Yeah. Yeah. That's a good way. That's a good way.
Really anyway.
Oh.
Okay. Let's go ahead and dive back into optimization. So last time I had started to discuss optimization, we wrapped up some things about nonlinear equations, which are necessarily part of what we do with a lot of optimization. And then what we do with optimization that goes beyond just solving nonlinear equations is we start off with some formula that I'm calling f of x here. That anybody remember what we call this? Well, it's the objective one, right? We have some objectives. A lot of optimization, the trouble is coming up with what that objective function is, because in many cases there are competing interests. And so it's natural to wonder, what if I have multiple objectives? Well, then you get into multi-objective optimization. And that's a class of optimization, but one way that you can consider forming an objective function when you have more than one thing that you care about is to weight them in some way and then add them. So as an example, suppose that you wanted to build a system that what would I want? What would my competing things be? Certainly, I want to minimize cost, and then I want to maximize like output or something. And you could put those together in an objective in some way. Like you want to spend as least money as you can to get the most gain. Or you can start to imagine that there might be like different trade-offs where together a low cost will lead to a low output, and that'll be one point. And then a lot of cost will lead to a lot of output. That'll be another. Where does the objective function point to in each of those cases? Because they both seem like plausible things that you might want, like low cost, low output. Sure, makes sense. High cost, high output. You want to find something that's in the middle. That leads to a whole bunch of things like Pareto optimum fronts or Pareto fronts, maybe things that you've heard about. Anyway, so there's a lot that we could go on, but let's just stick with these basic things where we have one scalar objective function that might be have vector inputs, right? But it still is just one function, returns one scalar value, one number. And then all the other things that we want to satisfy, maybe cost doesn't need to be part of the objective. Maybe the cost can be a constraint. We want to build this thing. We want to make the reactor that produces the most electricity possible that costs less than $7 billion. But something people would like, because I haven't heard a reactor price less than $7 billion in like 10 years. Keep going up. Okay. Maybe for smaller ones, right? And then we could also have equality constraints. Like if you think of something where you might have a problem that you optimize where something has to be exactly balanced. What would be an example? Remember, I told you all to come in with examples today, so I'm feeling you out for how much you thought about it, which doesn't seem like.
I have to
Yeah.
Optimizing a a group of isotopes that are decaying over time to find a certain isotope where a certain isotope is the most prominent in this 72-hour period that I'm looking at. So optimizing for an isotope needing a certain value. Yeah, I'm not here.
So what is the thing that you need?
We need a time period that is the most optimal to measure this certain isotope.
So you have multiple isotopes that are in a signal.
Yes.
They all evolve as a function of time.
Yes.
Yeah, I see. Yeah. And what you
just click.
so I saw the picture, right? So but let me annotate. So I've got some sort of a set of signals that we all. So what's T0? What defines T0? Like
taken out of the reactor.
Okay, so we've got a bunch of things that have been cooking, and then at time zero, they're removed from the reactor, and we watch things move in time. Some of them might grow, some of them might decay, right? Because some, if they decay, will grow into other things, right? So you might have things that look like regular old decay,
or you might have something that then builds up like this, and then it goes down, and then you might have something that actually builds up and then is, it reaches an asymptotic thing because it's the stable one, right? If these are number densities, and then the number densities then times like the decay constant would give you the activities that you would measure. And what you're trying to do is like, if you were looking for this red one, you want to know where the red one peaks
Mm.
or what.
Compared to the other isotopes, where's the highest point?
So you want to know where relative to say the black one, which also has a messy signal, where this gap is largest.
Yes, per se, to have the best result from that.
So you want the gap to be largest, and you want the means signal to be large enough too. Like it can't just be like a gap of like a large relative gap. It's got to be a large absolute gap, which adds. Yeah, so that's something.
Is that optimization? Yeah, I would say so, because you are looking for, as long as you can define that thing, if that's a gap here.
Give me a way to type text. They do, right? So if my objective function is maximize the gap, the max objective is equal to find t that maximizes the gap or something, right? Where the gap indicates like or correlates with a good signal, right?
And then what would some constraints on that?
Your time, your function of your isotope decay.
Yeah, so if you took it out at T0, you certainly can't wait forever, right? So that puts you might have some sort of practical thing like, hey, my time has to be less than 1,000. So if I needed T itself, if my unknown here were T and I needed it to be less than 1,000, can I write it in this form?
If you look at that the inequality constraint, it looks like it's a greater than or equal. But if I actually need
a time limited to something, well, actually we need a time greater than 0 too. So we can definitely have T greater than equal to 0, right? What's the function then? Well, no, the function, the constraint. If you're just saying, hey, my search space is limited to time greater than 0, and say time less than 100 seconds to make it explicit. This is cast in terms of an arbitrary inequality constraint, but I could use the identity function too, right? So if I put t greater than 0, that's the same thing as 1 times t greater than 0. That's the same thing as g of t is greater than 0 if g is the identity function, right? 1 time. That makes sense? So anytime that you have a constraint on the variable itself, that falls right in line with arbitrary constraints, where the constraints are function. And what about if I needed to cast this as t less than 100? Can I write that also as an inequality constraint in terms of greater than?
Right. So if I have something where I have a constraint that t is less than or equal to 100 seconds, how can I write that as in the form on the slide? Because, and this is not just to be trivial or pedantic. A lot of software for solving optimization problems will have a very, maybe not rigid, but a specific convention for signs. So what we will use from SciPy, the constraints have to be in the terms of greater than or equal to or equality. They don't have a second one for less than constraints, I don't think, right? But that doesn't matter. Why? Well, if I say that t is less than 100 seconds, is that the same thing as minus t is greater than or equal to minus 100? Right? So you can always transform your constraints to fit this build, right? That's going to be one of the things to consider as we go along. So honestly, the number of slides that I have after this, not a whole lot. It's the same ones that we were looking at last time. So I don't expect the material that's already prepared to take us the whole time. But I am also, I'll give you a little bit of overview what I'm thinking for the third project, which I need to get out now so that we have enough time. I'll save all discussion until we get to that point. But then we can also play around as much as you want with the optimization tool. There are a couple things that I'm looking at, but It's something where if you did come in with some real problems, it seems like Nick had one thing he's caring about, then we can solve those problems. I think that's kind of a fun thing to do, right? There's no better way to appreciate a tool than to see it in action for something you care about. Okay, so we've got the inequality constraints and then equality constraints. What would be an example of inequality constraint?
Where would we absolutely need something to add up or compute to zero?
Money.
It could be money. That could be like a budget line where the expenses must equal the income, right? Revenue must equal expenses, in some sense, right? Where, although one could also put that as part of the objective because maybe you just want to maximize the profit and that has to be positive. But resources in general, where you have finite amounts of resources, maybe we have a certain amount of uranium and a certain amount of steel, and we've got to make a reactor with it, right? So the total mass of steel has to be, the total mass of uranium has to be equal to something.
Or in that case, it would be something like if X were my mass of uranium, then it would be something like X minus, mass U is equal to 0, right? Yeah.
Couldn't you also say that with government or education? Where if you spend too much or spend too little, you mad at me.
Yeah, anything where you really need a line item balance, that's where you can do it.
In this case, it could be like maybe the total mass of fissile stuff has to be 0. So I could have something where if I had, let's say, 3 fissile, give me 3 fissile isotopes. U-235. That's fertile. What does it turn into? Yeah, so you got 233, right? So maybe I do something like X235, X2, I don't have to use X, but I'll say mass, M for mass. And then we'll just leave it as 235 and 233. We'll just keep it at that. Another one would be plutonium 239. Maybe this has to be true, right? Where the sum of your mass of 235 and your mass of 233 has to be equal to some combined mass. Maybe for whatever reason, you have to have exactly that mass. I don't know why you would in this case, but that would be the sort of that sort of constraint would show up very nicely as a inequality constraint. Okay. I want to get rid of the annotation. And there we go. All right. Now, when we don't have those constraints, things are quite a bit easier, and we can solve things using really just the derivatives that we've seen before, right? And so we saw this problem last time. I'll just kind of go over some of the tidbits that this highlights. This is a simple problem, right? It's just it's a polynomial. It's fourth order polynomial, so nothing fancy. But even this simple polynomial shows some features that show up in just about any real world optimization problem, or many of the optimization problems anyway. And it shows things like, hey, there's definitely a global minimum, but it is not the only minimum if our view is limited. So if we were looking in this vicinity, it might be the case that this local minimum is all that we find, when in fact we want the global minimum. This makes a huge, this is the main distinction between the types of optimization that live in that big, thick book I brought in, called convex optimization, and then things that look like this, because this is not convex. Basically, I can take a line here and draw it, and I am crossing it. I'm going inside or above to outside or below the line with a straight line drawn through. So if I have an objective function that, at least when viewed in a 2D sense, would not have this local maximum, then it would be a convex problem. What is nice about convex problems is that there are methods that are very well established for solving them, right? Because there is a well-defined global minimum. It's really just
you're diving down hills. And the only question is, how fast are you able to dive down the hill? Here, you can dive down hill, but it might be wrong. And so that's something that we can't address. So a lot of the problems that we care about, we will make the assumption that we can use the regular old tools that are known for convex optimization. When we hit problems that have really, really ugly objective functions, then we have to turn to other methods. Some of those are built into SciPy, and I have another example that I'll reference later on with respect to the project. All right, so we did solve this last time using Newton's method, so I'll go past that and immediately to the using the optimize function. So f again was that fourth order polynomial. The only thing that we needed to do in order to minimize that or find the x where it was a minimum is to call minimize with that function and then give it an initial guess. All of these algorithms, all these tools for solving nonlinear equations or for optimizing functions will almost always require an initial guess, right? And that's that. That's how we use minimize for a one-dimensional problem. Okay. The challenge that we saw right at the tail end last time is when we go from a single unknown to a vector unknown, we still have a scalar function at still taking one set of inputs and returning one number, regular number. Okay. When we take the derivative of that, we get g of x, which is the gradient, right? That's gradient of f, where we have the partial derivatives with respect to each of the unknowns. And then if we take the derivative of the gradient, we get what's called the Hessian. So the gradient and the Hessian take the place of the residual function in the Jacobian, right? In the nonlinear equation, right? And so we could call this a residual function, or the thing for which we want to find the roots, and we could call this a Jacobian. It just depends on what our frame preferences are. We starting from an objective function, a scalar function, or not. Otherwise, the math is the same. Okay. Why don't we actually? I'm going to inject an example here, and what I'm going to do with that is, oh, actually there is the example. I just hadn't put the fragments in. My bad. Okay, so let's take my. Oh, there we go. I have to scroll down. Okay, let's assume that we have an objective function that is this thing here. How would you describe the objective? I've got two unknowns, x naught and x1. I'm adding some functions of x naughts and x1s, and they're pretty simple, right? What would you call this? I would call it the two-dimensional polynomial, maybe. I don't know that there's a specific name I would say, but the terms are polynomial. Okay, so let's use an initial guess of x equal 0 equal x1 equals 0, and then find it with minimize. So I've given you here the starter code. Why don't you see if you can use minimize and find out what the minimizing value of x naught and x1 was. Use the example from a couple slides before that. The only difference now is we're giving it a multi-dimensional function, and we've got to give it an initial guess that matches that.
It's and concept.
I was up at 4 a.m. today.
I'll be up at 4 a.m. tomorrow. Does that count?
I mean, everything we do counts somehow. Okay, when you think you have an answer, turn to your neighbor and bet $10 that you're right. And shake on it.
Very long depends.
Which bet?
Christian and I were betting to was the last week.
Why am I not surprised I had to do with this?
I took it, yeah, I took the over on all of them.
Wait, so who was did I disappoint?
Well, no, because you were earlier than I thought. you were
Yeah,
gonna
okay,
be,
that's good.
but-
I'm glad. Serves you right.
All right, do we have any numbers? Yeah, I'm gonna go and run my cells up to that point so that I have everything.
High value.
So that depends on what the objective, or how the optimization problem is stated. So what is this asking us to find?
Find X.
Yeah, I think that's your answer, right? Of course, if you have X, then you can get the objective function value too.
I got 4/3 and 5/3.
Anybody else get 4/3 and 5/3? Scratching a distant value. It's been a long time since I've seen the answer to this problem. It's 4/3 and 5/3, all right.
Just finding those.
Anybody want to bet against that? I don't think I want to bet against it, so. Let's see if I get the same thing. So
We have the initial guess, so the only thing we need to do is use minimize. We give it the function that we want to minimize, and then we give it the initial guess, and that initial guess is f initial, and if we run that, we get a set of x values that appears to match what Alex got. And then the function is minimized there and has a value of -2 1/3.
What library is?
SciPy.optimize. So that would be.
Where did there's where I did it. So yeah, so optimize, the SciPy.optimize has several functions. In fact, it's probably worth taking a quick look at the things that it has. So I use my favorite trick of dir, right? Dir. Oh, not minimize, optimize. SciPy. Oh, I should probably import optimize dir optimize. All right. Oh, that's because that's the wrong function. Okay. So the things that SciPy Optimize has there are things like this that it starts off with an underscore. Many times that you see underscores in function names in a context like this, it means that it's there, but it's sort of like as part of the it's sort of background stuff like that you shouldn't, as a user, need to use. Right? It's there. You could use it. So as an example, Kobe law, that's an optimization algorithm. Right, and then Kobe QA would be some variant of that. There's also things like I see dual annealing. Annealing makes me think immediately of simulated annealing, which is an optimization technique. Dual might be something related to that. Then there's things like LBFGS. I recognize that as an optimization thing. LinProd, that's short for linear programming. That's a type of optimization problem that we'll look at right after we're done with this example. So lots of things that are sort of like the algorithms basically that you have access to, but the ones that we'll look for would be without the underscore. And then we have things like, well, it's actually still some things. Well, you might recognize that. What's that? Bisect. Bisection. Start from the left, start from the right, pick the center point, choose 1/2, right? We did that. Okay. What else do we have? We have Brent's method, which is a nonlinear optimization tool. There's curve fit, which we will see probably next week. We'll do our data modeling least squares next week and then wrap up this semester with some of the differential equation stuff. But just see a lot of the stuff there, at least squares. So the optimize module has really quite a bit of stuff in it. It's not just about taking an objective function and optimizing it. There are a lot of applications that really under the hood can be cast as optimization problems, right? And that makes sense then to put up all this stuff in it. This functional line search, we might remember when we were talking about Newton's method, how if you start in the wrong spot, your tangent line can take you way far into no man's land and you cannot converge. That line search is there as one way to go along that direction, but maybe throttle yourself a little bit so you don't jump off the board as one. Lots of tools in there. Just be aware of them. Be aware that they exist and that you can find them when you want them. Okay, so now go over here. All right. Is there before we move on, anybody else have you thinking over the weekend and have an optimization problem in something that they're doing or something they did or something they might want to do that fits the bill of unconstrained optimization?
I guess like you can have a shielding problem where you have some source strength and some like required geometry and you have to build a shield of some material that gets your dose rate to some level and minimize the cost of the shield.
So what is your solutions?
It depends on what you're trying to optimize. Because you can try to optimize fix the shield or the amount spending on the shield. You can change your material.
So I would think that something like a shielding problem necessarily has constraints, which would make it a constrained problem, which you could, so there are some constrained problems that you can get first ideas by not considering constraints. I just say, optimizer, please find the thickness that I need that optimizes. Now for shielding, that's almost always going to be the trivial solution of make it infinite thick, sure, right? But if you were thinking about having a thickness of material that is used for shielding, but maybe not for shielding directly, but for tailoring the spectrum, you can imagine there's probably a certain amount of water that you would put in front of a fast neutron beam to maximize the number of neutrons that pop out on the other side of the water at a certain energy, right? Because the more water you have, the more thermalization, the more neutrons are going to scatter down in energy. And so if you are specifically looking for 10 eV neutrons, there's probably an ideal water thickness. Like if that is specifically what it wants, that might be something. If it's just to minimize everything that comes out, then that seems like it's got to be infinity. But of course, we can't do that, so you put a constraint. But that's good answer. If I had a quick way to do that problem, I would do that as an example. If there's no way to quickly simulate how neutrons go bouncing in water, just take some simulation and you could do it, but it would take some more effort. But that would be a good example. Right? That actually gives a good way to describe constraints and then no constraints. Any other? Yeah.
Well, you can always do like airplane design, maximizing lift and having the minimum required amount of drag to the weight ratio.
Yep. Although I think constraints are pretty important there too, right? So there are a lot of not a lot of things that are strictly unconstrained. Although there actually you can, at least for convex problems, you can always turn a constrained objective function into an unconstrained one by using something that you might have learned about in one of those previous math classes called a Lagrange multiplier. Oh my God, that's
a calculus flat.
yeah, I feel like I feel like I got like stronger recoils than a row echelon. That's funny. Yeah, that's a tough topic. I'm still like, I've heard before by others like who go through the academic or live in the academic world that it took them 3 times to understand Therma or like that sort of thing. It 3 times to understand some like fundamental thing. What I enjoy about teaching is that I see it way more than 3 times. So like I get to a point where like my familiarity with this sort of material, although I'm a little rusty because I haven't seen some of this stuff in a while,
But if it's something that I've taught recently, there's a different, you feel it differently, think it differently. But yeah, Lagrange multipliers were one that I think I only recently started to feel like I owned it. I think that's a good way. If you own it, that's when you've learned it, right? And when you own it, you can teach it and things like that. Anyway, so yeah, there aren't a whole lot of things that are sort of naturally put in terms of no constraints, but there are tricks to do that. We won't get into that. I think what's better is we dive in and start trying out some of these tools that we have available. So almost all the time we'll have these constraints, and that makes things hard, but there are definitely some problems or some classes of problems that are easier to solve in practice because of the form of the objective function and the constraint. So one of them that is very useful is called a linear program. Now, linear programs have been around, well, I don't know, maybe they've been around forever in some sense, but the algorithms for solving them only showed up, I believe, circa World War II. A guy named George Dantzig came up with simplex methods for solving. There are other algorithms now, but that was fundamental for doing it. Now, if you want to know more about linear programs, you can you could probably look into the industrial engineering world. I think a lot they have a class over there that covers linear these sorts of problems. I got some books there. What's wrong with industrial? Oh, you don't like them. All right. All right. What? Is this the Imagineer joke? Yes. Oh boy. I'm recorded. That's terrible. I was just saying I'm aware of a joke. I wasn't making a joke. All right. Let's see. Let's use minimize, and we'll do it for a simple problem, and then we'll get on to the linear program. So let's consider a problem that is probably pretty easy to understand, and maybe it's one that you can answer without using minimize. But what we want to do is create a thin wall right circular cylinder with a given volume, and that in this case it's a meter cube. We get to choose that radius r and the height h. What do we want to, what we're trying to do, use the least material, okay? So what is it that what are we trying to minimize? And what's the constraint? Surface area is what we are minimizing, assuming the thin wall so that we don't have to care about surface on the inside versus out. So yeah, it's like sheets of paper, right? I see some books. I bet this is the kind of problem that you saw when dealing with Lagrange multipliers. This is a place where that would show up. I think we don't have to use it. We're going to use Python. Okay. So our objective function is the surface area. So what is the surface area of this right circular cylinder? We can assume it has top and bottom, right? So let's do the top and bottom. Those are circles. We all like circles. Pi r squared times 2 for the two areas. Right? So the thin wall that immediately should indicate that you take the area times T as being the volume of the material. Right, so you've got it in some foil that you wrap around, like I think of an aluminum can starts off as some flat piece of aluminum. It's got a thickness, you wrap it around. The volume of that metal making can is now the thickness of that times whatever the area is. Is that exact? No, but for thin wall, that's totally fine. Right? Okay, so we need to minimize the surface area while maintaining that volume. So what we can do is to define the volume constraint as a function. One of the g or h of x's that we saw in the basic breakdown. Okay, so what we'll do is take in x, which is going to be our unknown. I'll unpack it like I always do into the two things that we care about, the radius and the height. I'll compute the volume, so that'll be the height times the radius squared, and then I'll return 1 minus the volume. Okay, remember this is going to be a constraint, so this thing, when it's all said and done, has to be 0. The algorithm under the hood is going to be trying different values of x, and it's going to find that it's not giving a 1. It's going to use that information to figure out how to change and maintain that volume. We don't care what's going on necessarily behind the scenes, we just need that constraint to show up as zeros and all of them. And the objective function, same thing, unpack the R and the H, then I return the the top and bottoms, the 2 times pi r squared, plus the height times g times pi times r to get the outer. That's all we need to do. So
How can you use this to use minimize?
what I'd like you to do now, you've got ample time. If you don't know how to put the constraints in, how do you think you would figure that out? You were in the wild. And your instructor said, when you're in the wild, don't do achievements. Use help on minimize and figure out where you should put the constraints. And we already know where the objective function is. That's the very first argument. The constraints show up somewhere a little bit differently. And I want you to
Use help and figure out where that must be.
mentioned it before, but when you do help, if you have enough patience to scroll all the way to the end of help, there are usually some examples. And ideally, those examples are inclusive of just about all the typical parameters that you might pass to the function. From which you can documentation. There are some constraint examples given. The constraints have to be entered. So, as a rule of a dictionary? Yeah, so fundamentally, it's a dictionary. If you have more than one, then you have a sequence of them, a couple or a list or whatever. And then that dictionary has a number of required elements. What are those? Right. Yeah. We've got 2 types of inequalities. One is the, well, inequality, or sorry, 2 types of constraints. One is inequality, one is equality. And then we have the function that defines the constraint. That would be the g of x or the h of x from the sort of overview slide. And there are some other things I think that could be put in. I'm not sure if they.
What those are, let's see, where it is. So, okay, so then each of the constraints has four possible things, but we definitely need the constraint type and you need the function. You could give it the Jacobian for that function because just like an objective function, we'll probably be needing derivatives, and if you give it the derivatives, read the Jacobian, that can help things out. And then if that constraint function needs other arguments, we can pass it arguments, just like we've seen for some of the other. So let's go ahead and see if we can do this, right? So minimize. I'm going to give it my objective function. I'm going to give it an initial guess. I will call that x not is equal to. This is actually a good question. I'm going to leave that as a blank for now. And then we have constraints equal to, I'll put it in a tuple dictionary that has inequal type inequal. And then the function, which is the volume constraint, right? This sort of structure is something that you should, maybe you don't have enough experience with other languages, but you should appreciate this type of flexibility. Like we are giving functions to functions, and they're being passed behind the scenes for something else to use them, right? So not impossible, but hard to do this in something like C++. Right, so that's one thing where a language like Python is very flexible. Yes.
Since we're maximizing objective function, would we want a negative objective function?
Yes. Yes. Yeah, we would find that it funny answers if we don't do it. So that's a good question. Good question, good suggestion. And so we could do that. Is there a different way to do? Yeah, no, we'll have to take that and yep, good catch. So this is the actual area, but we want to minimize. No, that's it. No, this is right. We want this quantity to be as low as possible while keeping the volume.
But I thought we were keeping volumes but maximizing the size of the sheet.
We are minimizing the surface, the amount of material. We have, right? We want to create this thing. Yeah. But good catch. You should be aware of the sign of your objective and what you mean, because that obviously can lead you to some funny results. So I think this is good. Check one more time. Yep. Okay. So the last thing that I need to do before trying the call is the initial guess. Now, we could put in an arbitrary number, but if we're willing to do a little bit of work, we can at least give the optimizer a feasible starting point, right? If we give it something, if I gave it, say, a radius of 1 and a height of 1, both in meters, what's immediately a problem? My volume would be pi, right? If I had an R of 1 and a height of 1, pi r squared times 1, my volume would be pi. So I'd have a volume that's already way out of bounds, okay? So what could I do instead? I could divide that height by pi. I could give it a radius of 1 and a height of 1 over pi, and then I would have a volume of 1. Is that correct? Or I didn't have as much coffee today as I know, but would that be right? So we could try it with 1 and 1 and see if it argues, but it might be better, and we can check the convergence if we give it something that is feasible. But we'll see what happens. Oh, inequality constraints incompatible. Why is that?
Well, if I gave it a 1 and 1, I put that into my volume constraint. I'm going to get 1 minus the pi, and I won't have been less than. Oh, this is not. That's not an inequality. That should be an equality constraint, right? Let's see if that changes it. Rank deficient equality constraint. Okay. And then what I'm going to try here is if I divide this by 3.14159, does that change anything? Oh, look at that.
If I start off with something that is much closer to a feasible solution, then it takes me 35 iterations, but it finally picks out something that could be my maximum value. So initial guesses matter. So just back up. Originally, I put inequality here, but then obviously this should be a quality statement. If we have an initial guess that was 1 and 1, then our first volume is so far out that the volume constraint is totally exceeded. And it has nowhere to go from. Okay, so if we give it something that is feasible.
I wonder what would happen if we gave it something like 0.1 and 1. Right. In that case, the volume would be 0.1 times pi, which will be less than 1, but maybe it'd find something. We'll see. In this case, it worked, and it actually worked out in roughly 10 iterations. Kind of interesting. What happens if I go here? Yeah, it's still finding things. Now, are the numbers that I get the same every time? Appears to be sort of set at that. Question.
It's really funny because you input pi.
Just look slightly longer.
You could do is if so if we say, let's say height R0 is equal to 1 or 0.5, then that means that height 0 would be, so if the volume is we need that to be 1 divided by np dot pi divided by R0 double, right? So if we just pick an initial radius and then compute from that the height that matches it, that appears to work. And I could probably change this to anything I want. Is there a way to do that? Oh, that did not work. Why did that not work? Ah, that could be. Yeah, if you start very far from the optimum, you might run into that. So how would I change the number of iterations? I think it goes into the options, which is probably a dictionary, right? Let's see what help on minimize. Obviously, the documentation for this is not small, right? So it's a function that lets you do at that final. Oh, max iter options dictionary. So if I take this and I do options equal max iter, and I say that maybe I'll put that to 200. And you know what? I can actually do disp true in case we want more. We'll try that. Hey, look, it worked this time.
I only needed 112. Okay. There's almost always these. And you're already familiar with the basic idea of setting the maximum number of iterations. That's your trick to not be waiting for everyone to file, right? And then sometimes there will also be plagues or options to limit or produce more output, right? In this case, putting the disk to true gives us all these additional things. So this is useful stuff because this shows you a couple metrics that can be used to understand why a process takes as long, right? In this case, the number of function evaluations, that's 548. We did 112 iterations, right? So that 112 iterations means like 112 guesses for that optimum before it got to where it thinks it needs to stop. But it evaluated the function almost 5 times, many times as there are iterations, which means it's doing something to build up information to pick out what its next thing is going to be. That is completely dependent on the method that is used. If you look at the different methods that are available, some of that I pointed out before when we looked at the contents of the module, we've got let's see, Nelder-Mead, Powell, CG, which is short for conjugate gradient, BFGS, Newton CG, which is a Newton accelerated conjugate gradient. There's the Kobe law that we saw before. There's trust, there's dogleg, there's some trust region things. I'm not sure if what else there would be. So usually it will pick a default that works well for the constraints and the objective is what it is, but for the constraints you give it, it will choose a default one. Some of them don't work with equality constraints. Some of them don't work with constraints at all, I think maybe, right? So lots of things that you can do. So if you try using minimize to solve a problem like this and you run into issues, we've seen immediately make sure that your initial guess is sane. And try to make it feasible. If you can't find a feasible solution, how do you expect the algorithm to find a feasible solution, right? Then make sure that if you are failing to converge, check your iteration criteria, right? The max error, there's probably something for tolerance too. And then if that still is leading you to issue, then you will dig it and figure out, is there an algorithm that is not the default that might work well? And so Nelder-Mead is like an extension of simplex method, right? The basic idea is, we'll see what, we've got a little bit of time, we'll solve a linear program. But the idea is that it will sort of build a polygon around where the solution is. So it'll just keep enclosing this. And that's the idea of the simplex method for linear programs. With Nelder-Mead, because it is not a linear program, it will approximate the problem as a linear program by doing our favorite thing, taking derivatives and linearizing using the tangent line, right, to define those things. So a lot of details that you don't need to, you're not responsible for, but it may prove useful in the future when you have to pick the right tool from the box. Okay. So as an example of not responsible, I'm not going to list these sorts of things and have you tell me what they are on an exam or something, right? It will be much more generic, like what is an inequality constraint or something like that, you know, things that are not specific to what is listed in code documentation. Okay. All right, here's another example that we can solve. And this one is an example of a linear program. You'll note that the objective function has, well, it's got a certain form. What form is that? We've got two unknowns. And what is that objective function doing with those two unknowns? Multiplying them. Putting them in exponential functions. Or is it adding them together with scalar weights? Looks like a linear combination to me. Right? So a linear program starts off with an objective function that is a linear combination of your variables. A good objective function that might fit this is, you know, a project cost, right? Where you've got the cost of resources, the cost of people, the cost of bank loans, whatever it might be. All that is usually additive. So you can make an objective function pretty easily from that. Then the other feature of a linear program are the constraints. If you look at these constraints, what can you tell me about these constraints?
Do they share anything with the objective function? We still see just x0 and x1. How are they combined? Are they put into ugly functions? Are they squared? Are they multiplied by each other? Or are they're added together? It's a linear combination. So linear programs are those sorts of optimization programs in which the objective function, the linear combination of the unknowns, and the constraints are either inequality constraints or equality constraints in terms of linear combinations of the unknown, right? And it's this structure, the fact that it's all just linear combinations makes it, it always solvable. If there's a solution, the simplex method is one guaranteed way to find the solution. Okay. You can definitely define a linear program that cannot be solved, right? If I said that, if I had two constraints, if I swapped this and said x0 has to be greater than or equal to 0, and x0 has to be less than 0, those two things together cannot be true, right? So you can definitely have inconsistent or incompatible constraints. Now, one thing that is a little off here for the constraints is I have both greater than or equal to or less than or equal to. As we saw before, the canonical optimization problem is cast in terms of greater than, right? If I recall correctly, that's how I had written it before. Yeah. And so my guess is that when we write an inequality constraint, and if it's a mini prod, it's going to want it all in one direction. My guess is that would be the greater than. Right? So we have to look at the documentation. So why don't you go do that? Take linprog, which comes also from Optimize, and we'll take a quick look at its documentation. Now note, because this is an objective function with some constraints, we could totally use minimize to do it. But when we have a problem that has a special class of methods for solving that class of problems, it's usually a good idea to use them. Right? Because a linear program with the methods under the hood, we will get the global solution if there is one at all. What I'm going to do is I'm going to copy this little bit here. And I'm going to paste that up here because I think this gives kind of an interesting. Sorry, very nice looking, but. Yeah. So if you look at the documentation and render it in text, they actually cast it in a slightly different way than we saw before. Before it was all in terms of regular functions, which makes sense because that's the easiest or most flexible way to do business. Now we've got to figure out how to take our inequality constraint, which we see here is a less than or equal to. So I'm talking about that. Okay, how can we take these inequalities and turn it into a matrix times x less than or equal to a right-hand side? And then for the equality constraint, how do we write this single one as a matrix times x is equal to the right-hand side? Let's do that one first. How do we write this as a matrix expression? It's kind of an uninteresting one because it is only one row, right? One equation.
we have two unknowns, which means we need a matrix that has two elements to be able to, what kind of matrix will this be? What's that? A 1 by 2, right? So that would be,
What I'll do here is I'll do a right arrow. So the A sub equal is going to be equal to 5, comma, minus 1. So that A times the X vector, right? The two elements would give us that equality. Where did that go, right? Okay. And then what about the inequality constraints? Can we write that in terms of a matrix as well? It should be 3 by 2 because 3 by 2 by 2 by 1 gives us 3 by 1, which is what we have for the number of equations, right? So we know that we'll need these matrices. So let me first do A equal, and that can be NP array 5 minus 1. In fact, I'll make that an actual two-dimensional array by putting the double braces around. That makes sure that it's treated as a row. And then we have the UB, I guess, for this one. So array. And what was this one's shape? 3 by 2. Right? So what's the first row? Remember, this has to be A times X is less than B. So we've got the X0 greater than 0. So that's actually just, that can be anything. That should be minus 1 times 0. And then, actually, I should probably do the B eq 2 because that's just P by 1. And then the second one would be 0 minus 1. The third one would be 1 and a minus 1. So these things come from, if I want this to be X not less, X not greater than 0 means negative X not less than or equal to -0, which is just 0. Same thing for X1. So that's why you see a -1 here and a -1 here. And then this one already is less than or equal to, so that's a 1, a -1. And then I've got to make the right-hand side for those, which will be 0, a 0, and a 2. And then what do I need? I also need C, which is this first vector, the vector of weights. And so that is a 1 and a 2. I think that is all I need. Now, note, there are actually, I could have done this slightly differently, but I thought it would be better to show how to set these because there is also the limit on the range of X value. So if I have X greater than 0, X1 greater than 0, I could put an element U for those things, and that would be a 2-element array, and that will also be a 2-element array. I think it's fine that they should be equivalent. So let's see what happens. Anything else that... Do you see anything else that is obvious, anything that's obviously wrong about what I've computed? If not, we can try solve it. So linprog takes in the C, takes in the AUB, the BUB, the AEQ, and the BEQ. It has bounds if we want, and it looks like the bounds are actually not vectors, so that the bounds would be either apply globally, which could be fine, especially if you have a bunch of things that have to be greater than 0. This would be a reasonable bound, and it looks like by default the bounds are set so that these are positive values, right? So either way, this should be fine. Okay. Anything that I'm missing? don't think so. And then it seems like it worked.
So found Q is 0 and sorry, 0.2 and 0. One thing to note about this call to WinProp, we gave it all these things that we just compute. What is one major thing that is not needed that we did need for minimize? That caused us issues when we chose the wrong one.
Yes.
The initial guess. Why? Because linear programs are directly solvable, deterministically solvable if they have a solution. And it is also deterministically possible to show that there is no solution, right? So basically, as part of the iteration, if it gets to a point where it can't go further, it is guaranteed there is no solution, just based on the structure of the problem. Okay, so linear programs, great class of programs, and I had a whole course as an undergrad on linear programs. It included some other applications, but interesting subject, very important to industrial engineering for like optimizing logistics. I think that's where it came out of the work of Danzig, was all army logistics, flows of material and personnel and other stuff like that, and subject to pretty simplified constraints. All right, now in the last little bit of time, I'm going to give you kind of a little topical preview of what the project will be. I'm hoping I get the project out. If not today, it'll be tomorrow. Now, so first thing, because we are getting a little bit shorter on time, I have a feeling I'm going to err on the side of it being too easy. Of course, that never actually happens in practice, but I feel like that's where it's headed right now. You can argue with me if that's not the case. There are some different things. So first of all, what you'll be using is actually a new version that I'm putting together for something called PoroPy. This was something that I wrote back when I was in grad school as part of a class project. It's something that it was that basically the setup of the class was it was kind of like a fuel cycle class. As you heard that we have this fuel cycle class, so similar to that, and then everybody in the class had was responsible for implementing some simple computational model for some piece of the puzzle. And mine was optimizing core load. Right? So when you put fuel into the core, you've got to make decisions on how to arrange it, because the impact on the arrangement, the impact of the arrangement on things like the cycle length, which translates to how much money you can get while the operating, to peaking factors, like how hot is this relative to the average, which impacts safety and your gaps to safety. So very important thing. So that was what I did. So I'm re-implementing this stuff because it was kind of hacked together. You know, that's almost 15 years ago. And so I'm bringing it back. So now I started from scratch. I've written the core of it in C++ for actually all the core of this was all Fortran. It's the heavy lifting. So now it's in C++, and I finally spent over the past 2 days probably 10 hours refreshing my memory on how do I take a program written in C++ that I want to use in Python, where I write it in C++ and I say, hey, import this fancy C++ thing in Python as a module, and then do that on Windows. I can do that, there's no problem on Linux. But how do I do it on Windows? And how do I get poor students like Alex to wake up some morning to download it and try installing it? And it worked. He cried a little bit, but just kidding. So it worked. So what I need to do is add a few things that were missing from my reboot so that you can do a project. So I'm actually combining some. So it's there. It's just I want to make sure that for obvious reasons, I would not want to push something out for you to download and install if it were broken, because then I would have 20 broken things to deal with, and I don't want to deal with that. So you'll get more information on that, but this is where it starts from. And to get a flavor of what it is, if you look up PoroPy, you'll find, or if you look up this thing, so this was 22251, that was the project report, core loading pattern optimization. Yeah, that's a 150-page class report. So all you alls who think that sometimes we ask too much,
we might, but
What level was this class?
this was, I think it tailored for grad students, but it would have been cross enrollment, right? I went to town. So where does PoroPie come from? So PoroPie is physics of optimization, physics of reactors optimization in Python. But Poro is the word for reindeer in Finnish, and so PoroPie is like reindeer pie. That's like the cleverest thing I've ever done. Yeah, anyway, that's where it comes from. PoroPie is anybody ever eat reindeer? I did once, and then I was vegetarian for 7 years. Yeah. Yeah, I guess so. So you can take a look at this stuff, but really what this was all about for me is I wanted to take simple neutronic models and then be able to optimize it. So I'm trying to show you. So you might recognize basic layouts like this. This looks like 1/4 of a typical pressurized water reactor, right? With very little detail. Okay. That's a checkerboard where the red and the black and the yellow are all actually I can't remember. Yeah, those are all 3 different fuel assembly types. This is a computational model, so again 3 different fuel types. The question in core loading pattern optimization, suppose you have a stockpile of fuel assembly, right? Suppose you have this in a typical PWR, you have 193 assemblies. Okay, so if you are loading it for the first time, you've got some options, right? You've got some decisions to make. Okay. Now let's simplify all that and just say you are given 3 batches of fuel. You've got let's say you have 70 of each type, roughly 1/3 of the 193. Okay. How do you arrange them in the core to maximize what the core does? What's the proper objective? Well, the proper objective is probably make the most money. Maximize the money that you make while being constrained due to safety limitations, right? So one of the easiest ways to do that here is if you are accounting for depletion, is choose your objective function to be maximize the cycle. That's the cycle length is literally a time period, but that translates to an amount of energy, right? If you're operating at full power over that time period, you have made a certain amount of energy. Now, in order to be able to stay operating at steady state for a long period of time, you've got to have a balanced power. You can't be peaking in one location because then that fuel will be burned down, lose the uranium, things will get out of balance. So it turns out in this sort of problem, you're looking for solutions that are kind of uniform, right? And that's not easy to do. And so you'll be looking for an arrangement that will lead to the maximum cycling, but then how do you account for the safety? For a reactor like this, you will have localized ups and downs in power. Right? That's it. You can't avoid that. But what you can't have is a wildly changing shape in power. If you have in one location here, like suppose I zeroed in and I found that the average power of a given pin was 5 times the average of the power of all pins in the core. That would mean that this particular spot is probably 5 times hot because 5 times more energy. What's that going to do? That's going to send me way past my temperature limits. And so in order to bring that down, I got to bring down the power of the whole reactor. It'll always scale down at once. So the more uneven power you have, the more your overall power, your average power is reduced. So the closer you can make all powers to be the same, the more wiggle room you have between your lowest power and what your peak power can be. So that's one of the things that you can do with this stuff. And then you can start looking at solutions. So these would be some neutronic solutions for a little, essentially like a diffusion solver I wrote. Then it goes into all sorts of things about an optimization algorithm called genetic class called genetic algorithms. Anybody ever hear of genetic algorithms? Basically, it takes solutions and it treats them as though they were individuals in a population. And then by using some sort of fictitious mating, you can take parts of the solution from one parent, combine it with parts of it from another parent, and end up with maybe a better solution. What might that be in this case? Well,
you might find that a certain pattern of fuel assemblies in one region of the core works really well. And you might find that another pattern in another parent works really well, and to combine it levels off things. You can find combinations that end up increasing the overall fitness, is what they say, survival of the fitness. You don't need to look into it, but if you are interested in this sort of thing, I wrote another program as part of that project to support that project, which was a Python wrapper around something called PGA-PAC, which is a genetic algorithm implementation out of Oregon National Lab many, many moons ago. I haven't touched this in 10 years, so it might not be there, but it has some interesting background. And one of the examples is nuclear related. So optimizing a slab reactor. All this stuff for the folks who have had NE630 could read through it and probably understand immediately what a lot of the stuff is. You've got a slab reactor with a number of fuel assemblies, and you swap them around so that you maximize K infinity reactivity or K effective of the core. Okay, so it's that sort of stuff. You'll be doing a little bit different. So you'll be using this new version of CorePy that comes with some data models. One of those data models, and one thing that you will be focusing on for a good part of the project, is reactivity. So you've all heard of K, right? The multiplication factor, K equal 1 means steady state. Reactivity is related to K, so rho equals 0 is K equal 1. So you want no excess reactivity. Rho equals 0 means steady state. And we have data that comes essentially from two-group diffusion type stuff. And you can look at reactivity as a function of burnup. That's the amount of energy produced. That'll go down because the more energy you produce, the less uranium you have. And for your purposes, it's just going to be a nonlinear function. And with that function, you are going to explore things like how sensitive that parameter is to changes in some input parameter, like temperature. And that you can call in mind things like finite differences. So I'm not giving you an analytic function. I'm not giving you something that you can with pen and paper drive. So you'll have to use numerical methods. Okay. There will be a numerical integration exercise too to find something called the mean boron concentration throughout the cycle, and some other things. So I've got some moving pieces that I want to put together to make a compelling story for you all without it being too hard. So I'm hoping it'll be rich in content and fun in playing with, but not excessive in the amount of ChatGPT season you shouldn't be doing. None of this is busy for him. Anyway, that is everything I have for today. Hopefully you find something interesting in all this. We will meet up again on Thursday, and oh goodness, what are we doing on Thursday? I guess we might be moving into the least squares type stuff, which makes sense. That's a good transition point. So we'll have the people here will be. Oh, well, it'll be recorded. I'll have to think. The plan will be here on Thursday. I know that many of you won't be. If that changes, I'll let folks know. Okay. Who's gone? So probably, and from folks who aren't here, how many are gone, do you think?
And also grants.
So maybe roughly a third of the class. Yeah. So I don't want to plan to outright to cancel it. I don't think that's the right option. But if that changes, I'll let you know. Yeah, otherwise, have a good trip. Represent us well.
What do you think about having a project to do? What do you think?
It's after I release it.